Everyone, we've been talking about induced electromotive forces or induced voltages in current loops when there's a change in flux. But now we can have a induced EMF if we have motion of a conductor in a magnetic field. So our example here is the bar that's on this rail. The rail is attached with a resistor, and there's a magnetic field that's passing through. You can see that's shaded in area S. So the area is either in or out of the page. In this case, it looks like it's pointing in, so it's pointing the same direction as the magnetic field. The question is, when you give this bar a kick, if you kick it to the right and it starts to move, what happens? So as that bar moves to the right, you can think of this as the area increasing. As that bar moves down to here now, the area went from this small location right here that had flux to now this entire area. So as we are changing our flux, this time the magnetic field strength is staying the same, but our area is changing with time. So our induced voltage is going to be B dA dt as that bar moves down the line. So the first thing is to first figure out which direction the current is. Well, as the bar moves out, we're going to gain more and more X's in that area. So the bar is not going to like that. It's going to throw its own magnetic field dots out of the page to counteract that change in flux, which means current, if you put your thumb in the direction of the current and curl for your magnetic field, to get out of the page field, your thumb points up on this conductor. It means the currents flow in this counterclockwise direction around the loop. First thing we know is the direction of current. Well, to know how much current, we need to know the voltage. So let's start with the flux. The flux is B times area. Well, the area here is the length of the bar multiplied by the width of the bar. So let's say this distance x. So I can replace my flux with BA to be length times width. Remember that voltage is negative d flux dt. So I've got to put my flux in, and I get this. Magnetic field times the length times x over dt is going to be giving me my induced voltage. Magnetic field staying constant. The length of the bar is going to remain constant. What's going to change here is this distance, the dx, as we move over that. So dx dt becomes our changing value, and if we just do dx dt, we've seen something like that before. Change in position over time gives us our velocity. So due to the motion of a bar, this is why we call this motional EMFs, due to the moving of the bar, it sets up a potential difference in the bar, and you get the voltage to be set up as BL times V. Now that we know the voltage, if I want to find the current, there's a resistor over here that's going to dissipate that heat. Since now there's going to be moving charges and they're going to generate some energy, that resistor is going to heat up, and we can find our current by taking V over R, or our new induced voltage of the BLV. So we can see the reason we get this current is because of the moving charges and because of that change in flux. But there's another cause and reason we can explain why we see the same exact thing. If we were trying to visualize what is actually happening in that bar as it moves along, think of it like this. If we have a positive charge that's in the rod and it moves in a magnetic field, based on force equals QVB, you put your fingers in the direction of velocity, curl into the magnetic field, and you see that positive charges feel a force upwards. And now that we have a potential difference across the rod, there's a high potential at the top of the rod and a low potential at the bottom of the rod, or you could do left-hand rule and show that all the electrons are going to pile up on the bottom with QVB. We could then say that we've got a magnetic force pushing up, and now we have an electric force pushing down. Those charges, as they drift to the top of the wire, are going to sense all those positive charges above, and there's an electric field that's set up through the wire. So the magnetic force of QVB is going to be canceled out by the electric force if there's nowhere for those charges to go. Unlike in this problem, once we have the charges separate, there was a way to flow from high to low as they went through the resistor. So if I wanted to solve for the voltage that's set up across this rod, the first thing I would need to find is the electric field. Well, I know that the magnetic force here is going to be equal to the electric force, which means that QVB is equal to QE. And you can see there's charge on both sides. So if I want to know the electric field strength, remember it's velocity times the magnetic field. If I want to solve for voltage now, remember voltage is electric field times the distance of separation, distance of separation here is the length of the rod. So if I put in what electric field is right here, I get that the induced voltage becomes BLV. The same thing we just derived on the other side. So as long as I know the motion of the conductor, the length of that conductor, and the magnetic field, I can determine the amount of voltage that's created in that rod. So that doesn't seem too bad. We can find induced voltages, we can find the induced currents, and we can tell you how much maybe energy is dissipated in the form of wattage and power in that resistor if I know currents and voltages and even resistance. But there's one other thing you've got to think about in this setup. When currents are flowing around in this counterclockwise direction, because we have current flowing up the wire in a magnetic field, that current is going to feel a force based on Philb. So to figure out the direction of the force, put your fingers in the direction of the current, curl into the magnetic field, and you're going to see a magnetic force pushing backwards. So you go, okay, we have a magnetic force backwards on this wire. What's the big deal? Well, the big deal is that you gave the conductor a kick. You gave that bar a kick forward, and it started to move. And as soon as it started to move, it induced currents. It started to have charges move through the rod, and moving charges now feel a force against the motion. So what you've also created in this is what we call magnetic drag. There's a magnetic resistance to that motional EMF and motional current. So things that you might be asked here is, how long does it take that bar to get to a certain speed? Is the force constant, or is the force changing with time? Well, let's think of it this way. As the velocity decreases, that means that the change in flux is going to decrease. And if the flux changes at a particular rate, that means the voltage drops in that loop. Well, based on V equals IR, if the voltage drops, that means the current's going to drop in that induced loop. And if the current drops, that means the magnetic drag force must also drop. So this is not a constant force. It's not like friction where you say, oh, I just need a coefficient and a normal force. This force is changing every single moment that the velocity changes. So that's what we need to focus on. First, we need to figure out how the force responds to the induced voltage, and then figure out an equation for velocity as a function of time. So the magnetic drag force, we know, is going to make our mass accelerate. In this case, I'm going to put it negative ma because it's going to decelerate the bar because the force is against our motion. What's causing the magnetic force? The magnetic force here is going to be caused by ILB. Magnetic field strength is constant, that's into the page. The length of the rod here is something that's not going to change, but what can change is the current. So we have to figure out what that current is depending on. Well, to get that current, we need a voltage. Voltage is coming from a change in flux over time. Well, where's the flux coming from? The flux is the magnetic field strength times the length of the rod times the width of that loop, which is going to be changing every single moment as that loop gets bigger and bigger. That's our dx. Dividing that by dt, that means that dx dt ends up being our velocity, and the induced voltage is the BLV. Negative BLV based on the definition of Faraday's law. Great, we've got voltage. Let's get current. Current must be voltage over resistance based on Ohm's law. So that means that we've got the negative BLV over R. So that's our current. Well, our current is now going to go into our force equation. It's going to get a little bit messier, but we'll be able to get through it. So here you go. You got MA equals negative B squared L squared V over R. That is the force, the magnetic drag force that we are feeling based on the velocity of that bar. But now what we want to do is solve for the velocity as a function of time, figuring out how fast that bar is moving after a certain amount of time passes. We said lots of things are changing. This is going to be an integration here that we're going to have to do. To do the integration, remember the definition of acceleration is dv dt. So now what I want to do is get velocity and dv on the same side so that I can do my integrations like we've seen before. So doing a little bit of rearranging gives us this. dV over V gives us negative B squared L squared over Rm dt. So we're going to have to integrate both sides here. All those constants out front can stay out there. We're going to go from 0 time to any time t, and we're going to go from our initial velocity to our final velocity. So let's integrate both sides. The easiest thing to integrate here is dt. dt is just going to become time, and if we integrate 1 over v becomes the natural log of vf over vo. Put it in our two bounds. Now what we need to do is solve for vf. So we've got to get rid of the natural log. That's where we take e to both sides. Solving for final velocity gives you this. The final velocity is the initial velocity multiplied by e to the minus b squared L squared over Rm t. And we've seen things like this before with currents dying off. We're seeing a velocity now die off to this e to the negative exponent. So another way that you might want to write it is Vf equals Vo e to the minus t over tau, where tau is going to be the inverse of all those constants. And if tau is a time constant, that means that, like we've done before, if t equals tau, then after one time constant, that'll be e to the minus first, which means we'll be at 36% of our initial velocity. And after two time constants, we'll be down even lower, around 14%. So that means that if you do the unit analysis, and I'd like you to do that so we can talk about it tomorrow, that R over M, B squared, L squared, should give you a second. So this is what we mean by motional EMF. It is the induced voltages that are created in these loops because of a changing area as that bar slides and increases, or the amount of flux. As the flux increases, the voltage increases, which means there's an induced current that creates magnetic drag forces on that moving bar. So good luck. We'll talk next time.